A recent tweet by Elon Musk about convolutional neural networks versus transformers has the Twitter sphere all abuzz, mostly people asking what in the world he means. Well, I've been thinking about it a good deal in the last 24 hours, and I had the privilege to have a phone call with James Dauma, who knows even more about this than I do, and we have a possible explanation for what's going on. Let's take a look. Hey y'all, it's Dr. Know-It-All. I want to start with the caveat that we are going to be wrong about this. Whenever you're speculating from the outside, you're always wrong. It's just a question of how wrong you are. And also James was super helpful in helping me like crystallize this and actually teaching me some stuff that I was just like, oh yeah, that's a good way to think about this. So anyway, he was instrumental in helping me to understand what's going on. He was unfortunately too busy to come on the show himself, but he gave of his time to talk me through this whole thing. So basically anything that turns out to be right, that's him. Anything that turns out to be wrong, that's me. So blame me for all the wrong stuff and give him praise for anything that worked right. So let's start with the 27-word tweet that has led to all of this brouhaha. On June 30th, Ray for Tesla, and if you're not following him, you should, talked about how Chinese companies have been emulating Tesla in terms of their architecture and what they're working on for full self-driving, and how that indicates that Tesla may lose their competitive edge in China, or already might have. As Ray begins his tweet, Tesla rewrote its FSD neural network software using transformer algorithm in 2021. Then Chinese competitors did the same with transformer. That is a really interesting tweet, very important, but what's much more pertinent to today's video is Elon Musk's response, which is Tesla is shifting emphasis to diffusion for compute efficiency, but will probably drop even that. No company is anywhere close to Tesla in useful AI compute per watt. And then you can see at the bottom my hot take a couple of hours after this tweet. Interesting, given what we saw recently at CVPR, and if you haven't seen my talks on that, check out the links in the corner or at the end of this video. The speakers talked highly of efficient transformer usage there, but hinted that new models are being developed right now. Any chance we'll get an AI Day 3 where we can find out more? So first of all, big fingers crossed that we will get an AI Day number 3 at the end of September, early October, somewhere in that time frame, and they will find it acceptable to discuss these new directions in their research at that point. But in the meantime, let's do the best we can with the breadcrumbs we have. So the first thing is transformers versus diffusion. And when I texted James originally about this, he said, what you're asking is, what is avocados versus philosophy? He's like, these two things are not the same. And when I started thinking about that, I was like, oh yeah, you're right. One is an architecture or kind of more of an object, and the other is a process. So the best metaphor I could come up with, which seems highly appropriate, is cars versus transportation. So a car would be like a transformer. It is one way to do transportation, right? You drive around some place, you can get from A to B. You can do many types of transportation with a car, but it's not always the best way to do it. Transportation, on the other hand, is a whole concept. It's a process of getting from one place to another. So clearly you can use a car, which would be a transformer, but you could also use a boat, or you could use an airplane or a truck, or some sort of eVTOL or something like that, right? So there's lots of different ways to do transportation, and a car is one of them. Whereas diffusion is like transportation. It's a whole procedure. It's a method of doing something. It's a way of getting from point A to point B. So what's the difference between convolutional neural networks and diffusion? Well, diffusion, again, is a process, and the essential process of it, without getting into too much detail, and you can check out videos on that and transformers if you're interested, I'll put links to that up in the corner, is that diffusion is a process of adding noise to something in a diffusive process. So you could think about it analogously like putting food coloring into a glass of clear water. And what happens is you put in a drop and it diffuses around the cup until the whole cup is kind of a reddish color, assuming you put in red food coloring. So that's the kind of diffusion process that happens. And the whole point of diffusion is to back that process up. It's reverse entropy. And actually, interestingly enough, Veritasium just did a video on that today. And so I was listening to that when I was at the gym, and I was like, oh, that's highly appropriate. But anyway, so diffusion is actually anti-diffusion. What you're trying to do is remove noise from an image. So what you do is you take like a clean noise, so you'd have an image of me, and you progressively add noise to that image until you get to a point where you can't really see the image anymore. It's all noise. But you do it, instead of in one go, you do it in 50 50 steps or 100 steps or 1,000 steps. And so at each step, you're just adding a tiny, tiny, tiny little bit of noise. And then what you do is you teach the neural network to back that process up. So diffusion should actually be called like anti-diffusion, I guess. So what you're doing is you're backing the entropic process of diffusion up. You're reversing the entropy of the image to reproduce the clean image that you've got originally. And then if you integrate that with contrastive loss text embedding, what you can do is you can actually guide that process. So you can say, here's a bunch of noise, give me a human being, or here's a bunch of noise, give me a surfboard, or here's a bunch of noise, give me a koala bear in a tree, or something like that. But the basic foundational methodology of this is removing noise from an image, at least if you're doing this in image space. And within that diffusion process, you could use transformers or convolutional neural networks or another method. So it's actually kind of agnostic of what you actually do inside of it. Now, some things definitely work better than others, but the process of diffusion and reversing that process does not depend on anything. If tomorrow somebody came up with a great new neural network architecture called Orange or something, and it did something super, super cool, you could plug that into the diffusion model, whereas you can't really do that with a transformer because a transformer that's the architecture, that's the thing that you're doing. So you can see how these are different things, but that diffusion model generally uses convolutional neural networks. That's a very efficient way of doing it. So basically what Elon is saying in that tweet is that you're moving from a transformer attention-based type of model to a more convolutional neural network-based model. And this actually could be rather profound. One thing that's important to note is when you start talking about transformers versus CNNs or convolutional neural networks, in the AI world, that's actually kind of a religious war at this point. There are the transformer camp and there's the CNN camp, and they really, really hate each other a lot of times. So I'm not exactly sure why people get so philosophically concerned about their particular architecture. But anyway, I don't particularly care. Whatever works well for me. I used CNNs when I was doing my master's thesis work back in the late 2010s, because that was the state of the art at that point. But obviously transformers do really fantastic stuff, so I don't care. I'll use that now as I need to. But one really interesting aspect of this religious war is that people who are advocates of CNNs have shown over time that pretty much anything you can do with a transformer, you can remodel with a convolutional neural network. Sometimes it takes more work, more effort engineering-wise to get it to work right, but the advantage of CNNs is memory bandwidth and the ability to be executed very, very quickly on specific types of hardware, and that's going to be a very important point in just a moment. So once again, just to reiterate, transformers are an architecture that directs attention. It says, where do I need to be paying attention? And again, large language models are a great example of this and an easy way to understand this. In the image space, it's a little more complicated. So if you had a sentence something like, the orange cat sat in the red bed, what you can do is you can get to the word bed and you can say, what do I need to be paying attention to in this sentence? What's the most important word for that word in that sentence? And what you do is you back up to the word red, because of course that's an adjective that describes the word bed. So that's attention based, whereas diffusion models are ways of removing noise from an image to get a clean image, and you can be very creative with that. But they make use of convolutional neural networks. And what those do is those run a mathematical filter, like a little thing. You can imagine putting like a window on top of an image and running it across. And it basically just does multiplies and adds all across that. And it takes that image and it compresses maybe 9. So if it's 3 by 3, you could take 9 pixels and you could multiply and add and reduce those down to 1 pixel. So you're reducing the size of your image 9-fold by doing that. And then what you can do is you can actually add filter depth to that as well. Anyway, there's a bunch of stuff that you can do with CNNs, but effectively what you're doing is reducing the dimensionality in these dimensions and increasing the dimensionality in the other dimension. And that produces what's called a latent space, where you can play around with things like add noise to it, remove noise from it, do all of these kind of things. And then at the end, you do the reverse process or deconvolution to pop it back up to its original size. And of course, with diffusion, you can do it in a guided manner. You can actually tell it things that it should see. James likened it to two people laying on the grass looking up at clouds. And you know how if you look at clouds for a while, you can see shapes and stuff. But if one person turns to the other and says, "Ooh, do you see the dragon in that cloud?" that means that the other person is preconditioned to start imagining a dragon in that particular cloud. And the likelihood that the other person will see a dragon goes up dramatically. So basically what you're doing is you're telling the diffusion model to dream. You're saying there's a dragon in all of this noise. And it's like, oh yeah, I think there is. And it's as it reduces the noise in the image down and down and down, it produces something that looks more and more like a dragon because it's imagining that. So it's effectively hallucination, but like a guided hallucination where the human prompt tells it how to hallucinate. And the really interesting thing with diffusion is it's classifier free. In other words, you don't have to have a labeled data set to do that. So the old standby of dogs and cats, right? You have dogs and you have cats and they're labeled dog and cat, and you can teach a classifier network to identify dogs and identify cats. And it can do very, very well, but you have to have a labeled data set to do that. Very difficult to do with the giant world around you because the world is very complicated and it takes a long time to label things. Now, Tesla has created an amazing auto labeling pipeline. That's one of their major advantages they have. But one thing that diffusion can do is it can learn in a classifier free manner. So you can guide it by saying things like dragon and stuff like that, but you don't have to explicitly label a picture and say like, oh, that's a dragon. You give it a bunch of input pairs, which is language and images, but that's done kind of in a separate thing. That's what clip is. That's already been finished. And when you're doing the diffusion model, the diffusion is creating these images classifier free, which means when you train it, you give it the output image as the target, but you don't have to explicitly label that output image. You just give it the image and you give it a bunch of noise, and it has to drive itself to get to that image. You don't have to label that image. And not needing to label things is a massive advantage when it comes to the desire to scale. So if Tesla wants to ultimately scale, this would be a way that they could do that without having to have this auto labeling system in the pipeline at all in the future. Now, it's also important to note here that this is not James Dauma's opinion about this. He believes that they will need labeling for the foreseeable future, and that is quite possible. I could be wrong about this. So I foresee a world in which Tesla does not need to have explicitly labeled images, and that something like this model would be able to produce reality without explicit labels. James doesn't think that's anywhere in the near future, so we'll see. More than likely he's right and I'm wrong, but I just wanted to point that out because I'm very far out on a limb at this point on my own with this speculation here. But if indeed Tesla can actually generate reality and understand reality without the need for any labeling, that is going to be a really, really big deal. And of course, that ties into the world model stuff that I was talking about from Ashok and from Phil's presentations that they did at CVPR recently. All right, so why is any of this important? If transformers and convolutional neural networks work just as effectively as each other within the realm of, error bars or something, if they work generally about the same, why does it matter which methodology Tesla uses? And that's where the last line of Elon's tweet is so important. So let's read it once again, just to have that fresh in our minds. No company is anywhere close to Tesla in useful AI compute per watt. So I, as like a university researcher, I always just think like, can it be done? That's cool if it can be done. But for engineers, for people who have to ship real products, it's not just can it be done? It's like, can it be done? How efficiently can it be done? How much power does it take? How much time does it take? This is the kind of stuff as a CEO of a startup I'm actually coming to grips with. I'm having to learn about the engineering aspect and shipping a product as opposed to just, going like, oh, wow, it works in the lab. That's fantastic. So while transformers and CNNs both work fine in the lab, there are differences when it comes to engineering. And the really big difference, as James pointed out to me last night, was that Hardware 3's memory interface is slow. It's designed for the matrix multiplication and adds that are so intrinsic to convolutional neural networks without the really wide data pipe. And the reason for this, of course, is that 2017, 2018, 2019, when it was being developed, transformers weren't really at the forefront of what was going on in terms of spatial computing. So they would have built this for something like a GAN or an RNN or something like that would have depended very heavily on convolutional neural networks. So they would have built the chip to be as fast as possible for that specific instance. And specifically, Hardware 3 is optimized for convolutional kernels, which means that they gave it a small SRAM footprint so that it didn't really worry about transferring things back and forth to memory because it assumed that most of the bottleneck was going to be in the compute of the matrix multiplication and add, not in the memory store and retrieve stuff. But the problem with transformers is because they have very, very large windows, they're very, very memory hungry. And so you have to feed a lot of memory into the processor prior to it being able to process. And that comes down to engineering trade-offs, of course, that were made in the late 2010s that are not ideally suited for transformers. And as a quick note, Hardware 4 has resolved a lot of this. It's gone to very, very fast, wider bandwidth memory. I think it's GDDR6. That's really, really fast memory. It's got bigger bandwidth, more lanes of memory, etc. It's all very detailed, but basically Hardware 3 has about 4.5 gigabytes per second at 128 lanes of memory, whereas Hardware 4 has 14 gigabytes per second at 256 lanes of memory. So you're looking at a great deal more bandwidth of memory in Hardware 4 than 3, which is also, according to James, I don't know the details of this, but he says that's why the power envelope of Hardware 4 is too big to fit in vehicles that are Hardware 3 compatible, because they just don't have the bus that can provide the kind of power that Hardware 4 needs. So basically, if Tesla is going to solve full self-driving, the best methodology they have is to use convolutional neural networks. And like I said, the CNN camp has shown that basically anything you can do with transformers, with enough engineering work and enough tweaks, you can get CNNs to perform at that level and even potentially better than that. And if you can do that, that's going to be way, way, way more efficient on the millions of vehicles that currently have Hardware 3. That would be very, very difficult to retrofit to Hardware 4. So this is a great solution for Tesla from an engineering standpoint. So while transformers might be fine and they might work perfectly well in the lab, or if you had all of the compute power you need, when it comes to mobile compute, which is what's in your car, you want to use the most power and computationally efficient method possible, which is convolutional neural networks in this case. So how might Tesla go about implementing this? This is where we get to complete speculation at this point. So this is the part that's going to be the most wrong. I think we're actually pretty well on track with this beginning stuff, although who knows, we could be wrong about that too. But I think the speculation part is where it's most likely to go wrong, because we're really, really stabbing in the dark with this stuff. And the big clue that we have is the tweet from Tesla where they actually show the future being generated by an image system. So it's actually outputting the 8 cameras worth of views in a 2-dimensional space from past priors, from basically driving down a road up to a certain point, and then you don't tell it the future and it has to generate that. That is very effectively done, especially the 2D output, by a diffusion model. And so we could see that happening. So the likelihood is what you would take is some sort of latent space from the synthesis network. In other words, the stuff that reads in the photons from the cameras and uses regnets and BiFPNs and things like that to mash it down into a latent space. At that point, you take that latent space, and instead of using a transformer to do attention on this, you use a diffusion model to sort of denoise that image into reality again. And the way you would train this would be to give it the nerf output from the transformer, so you can use the transformer network to create a ground truth. So you give it a latent space input and you give it the ground truth output, which is the nerf from multiple cars driving in a scenario. And between there, what you do is, instead of using a transformer now, you add some noise to the nerf or things like that, and you push that back to the latent space. And then what it has to do is denoise that. The diffusion model has to use CNNs to go from the noisy latent space image to the ground truth nerf image. And that could be run backwards and forwards, but basically you can train this diffusion model, or again, this anti-diffusion model, to take a latent space and to create the reality of that through multiple steps, right? So again, as opposed to a transformer that kind of goes in one step, a diffusion model does multiple steps to get from the input noise source to the output reality that you're interested in. And yes, I do know that newer diffusion models do this in very, very few steps, down to almost 1 or 2 steps. So, there's a lot of research that's going on, but just the general idea is the diffusion model takes multiple steps to go from your input to your output, whereas something like a transformer generally goes in one step because it has a whole bunch of stuff stacked into one step. And another method that James suggested, which I think is pretty genius, is what they could do is they could go from the synthetic input space, that latent space that they get from the photons that come in, and they could use a basic MLP or multi-layer perceptron, basically kind of a dumb, fully connected network. It's not dumb, but anyway, it's a small one. It doesn't have to be that big. I guess that's why I'm thinking of it as dumb. But they can produce kind of a basic occupancy network out of that, a kind of low resolution version of that, and then they can use the diffusion model to upsample that into a high resolution version, which is an occupancy network that's actually usable in the real world by the cars and of course by Optimus, the Tesla bot as well. And of course, again, what you do is you use your transformer network that you've got now to build the input-output pairs. So you build that low resolution noisy MLP output and you give it the NERF occupancy network kind of hybrid thing at the end, and then you train it to go from this input to the output. And so you can use the network that you have right now to bootstrap up this new network. And again, if I'm correct, and it's totally my speculation, but if I'm correct, you can do this all without explicit classifiers. You don't have to have labels on this data. It will just learn to understand. And the advantage is if you don't have to have labels, you don't have to label everything. The world is full of crazy things. You saw Ashok talking about how complicated smoke is for occupancy networks. So a traditional occupancy network says, is a voxel in space occupied or not? Well, smoke is opaque, so you can't see through it. So it's like, is that filled or not? A human being's going to go like, I'm going to slow down a bit, but it's smoke and I'm going to drive through it because I know just from experience that that is not a real object that I have to worry about. It's just something occluding my eyesight that I can't see through very well. And that's something where an occupancy network is going to have an incredible difficulty figuring out between those two. But a world model, something that the car builds up from the ground up, where it just experiences life like a human baby, will be able to take those types of inputs and go like, I don't need a label for this. I just know that that thing, the thing that is smoke that's described that way in the human language, is something that I need to be more cautious about and slow down, but I can continue driving. I don't have to stop. I don't have to treat that as a solid object. So the ability not to have to put labels on things is pretty critical in my mind in terms of getting to the next step change in terms of the way that full self-driving works. The computer in the car and the Tesla bot needs to have a similar world model to what human beings have developed through experience in our own lives. But regardless of whether you need labels in this current version of things or in some future version of things, or what Elon means by beyond diffusion, that they'll move past that at some point, more than likely he's talking about new diffusion models that actually aren't diffusion models anymore because they're kind of like one shot. You can go from the noise to the output in one step instead of multiple steps. Something along those lines, again, highly speculative. But the important part here is we're talking about an engineering problem, not a fundamental research problem. And Hardware 3 is designed for convolutional neural networks, which is what diffusion models traditionally use. And I assume that's what Tesla is using in these diffusion models, assuming that they're using them. And if you're looking at max compute speed per watt, the diffusion models are going to give you that, whereas the transformers are probably not going to be able to ever get that far. And so now I've spent nearly a half an hour expanding upon 27 words that Elon Musk said. And again, like I said at the beginning, there's the likelihood is that things are going to be wrong in here. But of course, the hope is that it's not too wrong. It's just a little bit wrong, not completely wrong. But as James said, until we get announcements from Tesla that contradict this, at least we can entertain ourselves in the meantime with all of this speculation. All right, I hope you found this video fun and interesting and thought-provoking, and it helped to explain what Elon might be talking about here, I think is talking about here, between transformers and diffusion models and convolutional neural networks and all of that kind of stuff. I know I couldn't get into all the details of all those architectures, so definitely look up other videos about that if you're interested in more, but hopefully this at least gives a basic outline of what Elon was talking about with that stuff. If you did enjoy the video, please do like it so other people can find it, and of course consider subscribing for more of this kind of content. As always, a huge shout out to my Patreon patrons, my YouTube channel members, and of course my Twitter subscribers. Thank you all so much for supporting the channel in any way that you can, and if you want to join any of those, just check out the links in the description. And if you're interested in a whole bunch of really cool merch, check out our merch store. Link is in the description. We have Tesla bot t-shirts, the Tesla meme t-shirt, success is a possible outcome, 4680 battery cells. All of that stuff is on t-shirts, mugs, tumblers, and on. So check it out. And finally, don't forget we are both Tesla and Amazon affiliates. If you look in the description, you can see how going shopping for a car, a solar roof, a power wall, or anything on Amazon helps out the channel. In the meantime, I'll see you in the next one. Bye-bye.